Good morning, everyone, and good afternoon to our friends joining from China, and a warm welcome to everyone across the world. Thanks for taking your time with us today's webinar. My name is Shiru. I think people probably know me. I'm Vice President and the Head of External Relations at UKCSAE. As a non-profit association, we're aiming to build a platform for people like you and me who works in automotive industry to communicate. Just a little housekeeping before we start. This webinar has two parts, generally speaking, and then so presentation and Q&A section. Please keep mute in the first section, and in Q&A section, you're more than welcome to have your camera on and raise your hand, the little blue one in chat area. And then also, if you're a little bit shy, you just want to question, but without actually using the audio, you also can send your question to UKCSAE host. It is the honor today we have Dr. Mark Peckham with us today, with the director from Combustion, sharing his experience in transient emission during the real-world driving. Personally, as a calibration engineer, I'm really appreciated that we can have this opportunity today to join this webinar talking about the transient emission in RDE topics, especially with someone like Mark who is really experienced, and then the automotive industry. I think maybe many of you have the same feeling as me. So let's see, is this the time for me to pass it to our host?
Yeah, thank you, Shu. Morning, everyone. My name is Transient. I'm the Vice President of UKCSAE and the head of the event organization. Again, warm welcome and thank you everyone for spending time on a weekend with us again. So today's, as Shu introduced, our webinar's topic is transient emissions during real-world driving with Dr. Mark Peckham. Very brief introduction to our agenda today. After this introduction and some latest information for our society, we'll go straight into the presentation with Mark. And after that, we'll have 30 minutes of the Q&A section. And as Sue briefly said before, we are inviting you to ask your question directly to our guest speaker. If you would like to just send the question to our UKCSAE host account through chat, we'll pick out the questions from the audience and then you can interact with us. So a little bit about our society. As many of you attended our events before, we are a non-profit organization connecting the Chinese community of automotive industry in the UK. We try to promote the exchange of support among its members and associated partner organizations. We plan to host annual industry level summits, regular online, offline technical seminar, as well as networking events. We currently has over 370 active members from over 50 companies and organizations across the UK and China. If you want to know more about our society, please go to our website, www.ukcsae.co.uk. Something exciting is coming up. As we mentioned in our previous webinar section, we're going to host our annual conference. This is now officially confirmed. Our annual conference is not only to celebrate the 1-year anniversary of our society since our founding ceremony in London last year, but also a technical forum for some of the most challenging topics in auto industry at the moment. This year, the discussion will be focused around automotive digitalization and the new energy vehicles trends in the UK. We will have a lot of panelists across the industry and academia from UK and China, and some from even from the Japan and the US. So please looking for that and save your day for our annual conference. It will be on October 31st. We're currently in cooperation with Association of British Chinese Professors and also University of Birmingham. We're looking for more partners and sponsors for this event. So please send your interest through our UKCSAE email or go to our website for more information. Now, without any further ado, let me introduce our guest speaker for today, Mark Peckham. So Dr. Mark Peckham graduated from Edinburgh University in 1990 with a first-class mechanical engineering honours degree and went on to Emmanuel College, Cambridge, to study for his PhD under Professor Nick Collins, completing this in 1993. After a brief spell at Ricardo Consulting Engineers, he joined Combustion in Cambridge, where he became a director in 1998. His current work involves the development of new measurement techniques and the new equipment with particular emphasis on real-world driving emissions. So Mark, warm welcome to you.
Well, that's very kind of you. Thank you very much, Peter, and good morning and good afternoon to you all. And I guess one of the first jobs I have to do is to first of all switch off my video, because you really don't want to see me for a long period. And hopefully I can now switch to my presentation screen.
Okay.
And if you would be so good as to let me know that you can first of all see my presentation screen and also see my mouse moving. Is that working yet?
It's getting out. Yes, it's working now.
Perfect. Right. Okay. And you can also see my mouse?
Yes.
Great. Okay. So shall I proceed?
Yes, please.
Okay. So thank you for so many people for organising this. That was very kind of you. And so today I'm talking about transient emissions during real world driving. We've been doing a fair amount of this at Combustion. And just to give you a little bit of a background as to Combustion itself, we're a company which is a spin-off company from the University Engineering Department in Cambridge. And that happened in 1987. And we have two divisions. We have the consulting division, where we have 8 transient engine dynamometers capable of running a variety of drive cycles, some of which can go to freezing temperatures. And we also have a chassis dynamometer with a robot driver. And our main focus within that division is emissions calibration work. So we do a lot of work on SCR systems, DPFs, cold starter gasoline engines, and very much a focus on emissions. We don't do any NVH work, durability work, all emissions. The products division, which is where I sit, we develop, manufacture and support a range of specialized emissions analyzers, including fast response hydrocarbon, NOx and CO2. We also produce fast response particulate analyzers, which can measure the size and number of particles. And we're talking about the specialization being fast response, we're talking about of the order of milliseconds. And we also produce a system which will test particulate filters. But what I'll be focusing on today is I'll be confining the talk to the gaseous pollutants of hydrocarbon, NOx and CO2. And really amongst those pollutants, I'll be focusing mostly on NOx, because that appears to be of the major concern for, well, both gasoline and diesel engine manufacturers, but also in the wider community, the air quality concerns in cities, which is driving a lot of the emissions legislation, seems to be coming down quite hard on NOx and possibly in the future on ammonia, and I'll touch on that a little bit later. Now, what do I mean by fast response? Well, I've got here a little bit of data, which was, this is real data, but what I've done is I've animated it. This is one of our fast response FIDs. So this is measuring hydrocarbons. And this is data that was taken from the exhaust port from one of the cylinders of a 4-cylinder port fuel injected engine as the engine is starting. Now, if I play this animation, Peter, can you see this moving? Is this animation working okay?
Yeah, it is working.
Great. Okay. Well, the green trace is cylinder pressure. The red trace is hydrocarbons. So what we're looking at here is we're recording data on a millisecond response time, and we're looking at what's happening to the hydrocarbons with each and every exhaust stroke. So obviously this would not be possible to measure this level of temporal detail when if you were looking at this with a conventional analyzer. So for example, what we've got here is the engine starts. We have 5 firing cycles as indicated by the high peak pressure, cylinder pressure. And then we have 2 misfires. And as soon as the exhaust valve opens from this misfire, you can immediately see very high unburned hydrocarbons. And then if I continue, then there's a burning cycle, then another misfire. So this is, this is an old engine calibration. Obviously, gasoline engines don't misfire these days. But you can see how quickly the instrument responds, and how, in this application at least, you can see what's going on even within a single exhaust stroke. Okay, so that is a kind of rather advanced application of our equipment, I suppose. For real world driving emissions, you don't need to look in that level of detail. But the main thing about real world emissions is that the real world is full of transients, and they're also unexpected transients. So you can calibrate your engine to the European drive cycle or the WLTC, but within certain boundaries, the real world driving emissions legislation can contain a lot of unexpected transients, which for the calibrator can be a real challenge. And transients can occur with a duration of much faster than 1 second. And therefore, if you use equipment which has a response time of much longer than a second, it's very difficult to identify and measure and quantify those transient emissions. And what's worse is it's very difficult to correlate that spike of emissions with whatever engine parameter is causing that spike. So if you take the standard PEMS equipment, which is very accurate, but it has a response time of a few seconds, and not only that, the sample line takes its sample from the very tailpipe of the vehicle, and therefore, as the engine has produced its emissions, it's burned the fuel, it's produced its emissions, the exhaust gas has passed through the catalytic converter, but most importantly, it's passed through the muffler. The muffler is just like a big mixing volume. And so all of the transient emissions, which have been produced by the transient operation of the engine, have been mixed and obscured and delayed through transit through the exhaust system, including the muffler. Now, we thought at Combustion, okay, well, we have these fast response analyzers already. Maybe they would be useful to be deployed in real world driving missions, because they can truly pick up on the transient emissions. And if we position the sample point at least before the muffler, so there's not much mixing in the exhaust system before the sample is taken, then we should be able to have a close correlation between the spikes of emissions and the fuel ratio control, the spark timing, the valve timing, all the other parameters which may have an impact on creating those emissions. So we took our standard analyzer and we miniaturized it as far as possible so that it could be carried on board a vehicle and could be powered from a separate 12-volt battery. And we developed some longer heated sample lines which yielded a response time of still less than 10 milliseconds. And also we developed some logging software which could bring together the analyzer emissions output alongside GPS position information and the OBD CAN signal from the vehicle itself. And bringing these 3 things together allows one to identify what are the problem conditions for any particular vehicle. So we will take a vehicle out on an RDE route which we developed around Cambridge, which contains an urban, a rural and a motorway portion, and we will look carefully for the positions and the engine operating conditions which create pollution hotspots. So here is a little bit of data from, this is from a new generation of diesel engines. So this is one of the Euro 6D vehicles. And you can see that if I put my mouse over event number 35 that you can see there, this is our starting point. This is combustion. So this is where we warm up our instrumentation and we calibrate it just before we start the engine and we drive off. But you can see that this color coding, the parts per million of NO is indicated down the scale on the right hand side. So this is just in parts per million at the moment. But you can see that most of the emissions events in the whole drive are actually associated with a cold start and the SCR system, which is on this vehicle, heating up. Now, this is one particular day, and here we are at event, which is seen there as event number 35. This is the start at combustion. We go anti-clockwise round this loop, and this is all urban, so this is all low speed. And then by the time we get to event number 27, this is the acceleration into our rural portion. So there's an acceleration here because we can now speed up to maybe 50 miles per hour. And there are a few twists and turns, and there are 1 or 2 hills and 1 or 2 junctions. And then when we get to event number 28, this is us joining the motorway. And then the large ring on the outside here, this is our motorway portion. The RDE cycle finishes at about this point, and after that we're just making our way back home at that point, at which point we check the calibration, we check for drift, but this is the route that we run with all of our vehicles, and it gives a nice blend of some hard accelerations, some very sluggish driving. But from one day to the next, because it's the real world, you have some variability. So if I flick forwards and backwards through the 3 days of doing this test, you'll notice that the events and the position of those events change quite significantly. And that's just because from one day to the next, maybe a cyclist or a bus might pull out in front of you at some point, which will change the position of where those emissions occur. But on this 3rd day, this was quite interesting because as the vehicle had joined and had settled into motorway driving, the DPF regenerated. And while it was regenerating, there was significant quantities of NOx being produced. So on this day, we had, I think, 47% more NOx emitted from the tailpipe because of the contribution to that regeneration event. The other advantage we have is if we have fast response and we have accurate GPS, then we can zoom in to an accuracy of, I think, about 15 centimeters at 30 miles per hour to identify exactly whereabouts we have emitted the position where we've emitted our NOx. So what we're looking at here is the first roundabout that we arrive at after leaving combustion, when the SCR system, the after treatment system, is still quite cold. But you can see there's an emission of NOx as we accelerate onto the roundabout and as we accelerate off the roundabout. And then when we change gear, there's another burst of NOx is being produced here. So you can identify exactly where the emissions are being produced. And for those involved in air quality, they really value these plots that we can produce because they can then start to predict, after building up several circuits and with different vehicles, where the likely air quality problems may be occurring from whatever their blend of vehicles are that they're interested in. So in terms of a process, what we tend to do if we have a new vehicle to assess and to identify any calibration work that's needing done, step 1 is to log the RDE emissions on road. Then our software will identify where problems are occurring. And because we're logging a variety of ECU parameters, we can then identify what may be causing those emissions problems, and we can translate and rerun those same portions of the drive cycle we have run on the road. We can bring them back into the laboratory, so under controlled environmental conditions we can repeat those transients. And really the only way you can solve calibration problems is by putting the vehicle onto a dynamometer under controlled and repeatable conditions, change the spark time, the fuel injection timing, etc., the EGR rate, and then take the vehicle back out onto the road and repeat the test again and see hopefully what improvement has been made. So this is a typical method we would use to do that. So to go back to the basics of a gasoline three-way catalyst, the three-way catalyst will take the legislated pollutants coming out of the raw gas of hydrocarbons, CO and NOx, and it will blend them over a hot catalyst to these nitrogen, water and CO2, these benign products. But this will only happen if the catalyst is hot and if it's fed with a balanced ratio of pollutants, normally from the engine burning its fuel at lambda-1, so it's stoichiometric combustion. The catalyst also has to be sized properly and loaded with the correct amount of precious metal. So if you have a rather low cost or cheap catalyst, if you give it too much flow, then those pollutants will start to appear in the tailpipe. And also when the catalyst has been aged and has had some damage and perhaps has been poisoned by some toxins, then also they don't tend to work very well. And the transients we tend to look at, I have to say that for most of the gasoline work we do at combustion, I would have said probably about 75% of it, we're really only looking at the cold start, the catalyst heating strategy, and then the rest of the drive cycle is basically to condition the engine for the next cold start that we'll repeat in 2 hours time after some rapid cool down. But the cold start, that's a wonderful transient to look at and really needs fast response equipment to pick up all of the transients inherent within the cold start. And then accelerations, decelerations, where there is probably some decel fuel shut off. And a gear change is really a blend of accelerations and decelerations. So if we now compare the data that we get from a fast NOx analyzer on board the vehicle, I've shown this data in blue, and I've also shown in green the lambda that is being logged from the engine management system. And during this drive cycle, which was kindly run for us at Marla Powertrain in Northampton, you can see that the control of lambda is around lambda-1, but during deceleration, lambda goes very high, obviously, because there is no combustion, there's just air washing over the lambda sensor. But when combustion restarts, lambda comes down, maybe the engine operates a little bit rich, sometimes a little bit lean, but it approaches lambda-1 as it should. But this control of how lambda is approached after a decel fuel shutoff is absolutely key. And you can see from the fast NOx analyzer, and this is measuring before the muffler, but after the three-way catalyst, on a production gasoline engine, when the engine restarts, it does tend to produce a short duration spike of NOx. And in this one at time 1019 seconds, that spike of NOx is really quite significant. 2,800 parts per million is the spike there. At exactly the same time, we are measuring with some PEMS equipment, which is bolted onto the back of the vehicle. There is a conventional analyzer measuring in the CVS tunnel, which is also connected to the tailpipe of the vehicle. And there's an FTIR in there as well. Now, all of these instruments are measuring the same gas in their standard way. The fast analyzer, though, you can see the spike of NOx. You can correlate that immediately with the start of combustion following that decel fuel shutoff. And if I were to plot on there the spark timing, the fuel injection timing, the EGR, etc., because they are all already time aligned, you can start to change these parameters and see if you can minimize bring down this spike of emissions. Now, the other instruments are also measuring that same spike, and they're measuring it accurately, they're capturing it, but because they have a much slower response, maybe 1,000 times slower, this is smoothed out, the peak is not so high, and it's very difficult to identify which of these lambda transients is associated with this hump of emissions which are being recorded by the slower analyzers. Okay, so I'm hoping that that will illustrate the main differences in the data which is available from fast and slower instruments. That's not to say they're not accurate, they're very stable, they're very sensitive, but their response time is much slower. So if we translate this into some real data taken from after the three-way catalyst, this is on a rather old vehicle, it's a Euro 4 gasoline engine, but in the upper graph here, I'm going to scroll this data. You'll see lambda sitting at about lambda 1. We've also got the HEGO voltage that you can see in purple. But down in this bottom graph, which is the main one where the action is going to be taking place, this is the instantaneous NO in the tailpipe data, and you can see how this will correlate with the lambda as I roll the video. So this is going over a speed bump in front of a school. So we decelerate towards a speed bump, then we put the clutch in and the engine restarts at idle, and you get a little start of combustion bump there. But as you accelerate away from the speed bump, there's a big spike in NOx, and then another little spike when there's a gear change. Now that's happening in real time. If we run the whole data at half real-time speed, because you know, as I say, everything happens so quickly, if you don't log it quickly, you'll never catch this. So here's our decel fuel shut off as we approach the speed bump. Then the clutch goes in, the engine restarts, but only at idle, so that's quite a small blip in NOx. But as we accelerate away from the speed bump, the engine should start with a rich purge to condition the catalyst, but it's not rich enough, so there's a fair amount, a 1400 ppm spike of NOx comes out, followed by a gear change and another little spike of NOx. Did you see that video, Kay? Did it run nice and smoothly?
Very smoothly.
Great, okay. Right. Okay. So that's a rather, in one way, it's a rather simple maneuver, because all we're doing there is going over a speed bump. But if you can imagine the real world and the entire 1.5 to 2 hour journey, it's full of these kind of transients. So these spikes are occurring all the time, or potentially could be occurring all the time. The other amusing thing about this is that the speed bumps were put in Cambridge on this road directly in front of a school to save children from being hit by cars, but it's probably increased the local air pollution by a factor of, I don't know. I mean, when a catalyst is working and the engine is running at steady state, there is almost zero emissions, but when you go over a speed bump, you're increasing it to 1400 parts per million. So there we go. So we can all argue with our local councils to remove speed bumps now. Now, calibrators always want one thing more than you have offered them, and the first thing I was asked for was 2 channels, because the calibrators would like to know, okay, you can show them what's coming out of the tailpipe fast. What they would also like to know is what's coming out of the engine before the catalyst. So here's a little bit of data taken with, our standard instruments are all 2 channel anyway, but the red trace is the instantaneous NO before the catalyst, and the blue is after the catalyst. And during this acceleration and gear change up a hill in Cambridge, you can see a nice oscillation coming through here from the closed loop lambda control, and you can see the oscillation causing some breakthrough into the tailpipe NOx. So again, the catalyst is nice and hot. This is a good 45 minutes into our RDE drive, but you can see there are significant areas where the catalyst is doing virtually no conversion, but they only last a short, you know, maybe less than 1 second. So fast response really comes into its own there, because you can identify exactly where and why those emissions are occurring. Now we move on to a little bit of work which is some quite good news, I suppose, really, for the automotive industry. Some work we did around London for Transport for London, and this is their route, which is called their West London route. And these were 3 separate days with 3 separate vehicles. And we start in North London at a place called Brent Cross. We go round London through some quite slow urban traffic. This part lasts about maybe 1 hour 45 minutes. And then as we approach the end of this city section, we then join a motorway. This is the M1 motorway. We join this on an up ramp and we go up the motorway for 4 or 5 miles. We turn around at a roundabout, we come back down, and that is the whole journey. But what I wanted to show you here was how things have improved. So this is the instantaneous NOx parts per million, which we logged in terms of its GPS position from a Euro 5 diesel and then from a Euro 6B plug-in hybrid electric vehicle. This is actually a Toyota Prius from 2016. You can see that the evidence of where the NOx is occurring from that vehicle are confined to really only 3 areas. And these are 3 areas where the vehicle is being driven in a way that the vehicle emissions control system doesn't react very well. And the Euro 6D temp diesel, so the kind of latest generation, there are very, very few instances of any NOx emissions there at all. There's a little bit where the engine has started and moves away at Brent Cross in the north, but the rest of it is fairly smooth. So you can see how much improvement has occurred as vehicles are getting newer. And if we translate this into the grams per kilometer, sorry, milligrams per kilometer, if we can log the exhaust mass flow rate at the same time from the vehicle that we're measuring the fast NOx, we can combine those two together and give us our cumulative NO emissions or NOx emissions. You can see with the Euro 5 diesel, so it has no NOx after treatment. The only thing which is preventing it from emitting NOx is its external EGR and to some extent its fueling control. But you can see that all during the 55 kilometers of that London drive, there are NOx emissions being emitted at all times. With the Prius in red here, you can see that the emissions are limited to those 3 areas that you saw on the map. So if you could solve whatever is causing those increases in emissions, then that vehicle would also be very clean. And the Euro 6D temp diesel, that's down at 60 milligrams per kilometre. But everyone can pat themselves on the back for showing how modern vehicles are so much lower emitting in terms of NOx. And I did make that point very forcefully for Transport for London, because it is on the basis of their perceptions that they will put in taxation and they will put in measures and fines for people entering urban areas, depending on the pollutant potential of their vehicle. Let's take a little drive through one of those areas in London which were producing significant amount of NOx. So what I'm going to show you here with this video is the lambda that we recorded from the vehicle's own lambda sensor. So we got this through the OBD port, the ECU, the diagnostics port. That will be shown in green. Down in the bottom here, I'll show you in blue the instantaneous NOx emissions, which are measured, this level on the left here is actually grams per second. So we're measuring the mass flux of NOx, I suppose. But what to look out for in the bottom right, this is the power indicator that you have on the dashboard. When the vehicle is in EV mode, that's with the engine switched off and we're just driving on the electric motor. But you will see as we drive through this area of London, which is quite congested, and there are a lot of lane switching required, that this will change from EV to just a hollow car shape. That's when the engine starts, and this is the power indicator. And some of the starts are under fairly high load. So I might accelerate here. Here's the engine starting. Here's my lambda. And here is a spike of NOx that's being produced. And because I'm having to negotiate through traffic, I'm having to accelerate past trucks, the lanes are quite narrow, the engine is starting under load, and our lambda control is starting slightly rich, but then it is drifting lean. And the whole problem there is with a three-way catalyst, if you allow the engine to operate for any significant amounts of time lean, then NOx will pass through the three-way catalyst without being converted. So here we're coming to a part of the road where two lanes merge into one, and therefore I have to give way to, surprise, surprise, it's a Prius taxi driver. I've been forced up onto the pavement. I now accelerate. Notice this lambda, the engine starts slightly rich, but then it drifts lean, and it drifts lean for a few seconds. And this is when my NOx is being produced. Now I have to turn right, but I have to drift across 3 lanes to get into the left-hand lane. And while I'm doing that, I'm having to look for a space between the traffic. There's lots of hard accelerations and restarts happening, but all the time, the engine is switching off and on, and when it switches back on, it is being allowed to drift lean. Now, this engine is a port fuel injected gasoline engine. Calibrating those is a little bit difficult because there's a bit of a fuel delivery lag, a delay to the cylinder. I expect a GDI version of this would be much faster and much better in terms of arriving at its lambda 1 condition. But you can see how that particular part of the drive, because it was requiring so much active acceleration, deceleration, and sometimes quite harsh accelerations, after the engine had switched off and was in electric mode and then was restarting, it was really because of that that it was exercising the transient fueling control really quite harshly. And I mentioned before there were only 3 areas in London where this vehicle, which otherwise is extremely clean in terms of NOx, the 3 areas, there was this one in Swiss Cottage. The other 2 were both where there were series of speed bumps. And with a speed bump, decelerate, over the speed bump, accelerate. The same sort of transients and the same fueling control problems are evident at that point. So we can zoom into one of those other areas in West London. It's a residential area. It's quite low speed, but what the council has done is put in some speed bumps. You can see we're traveling here from left to right. Here you can see the, sorry, let me just go back a little. You can see the speed bump. If I go forwards here, you can see the speed bump and you can see the spike of NOx emissions which occurs as I accelerate away from the speed bump. So that there looks as though it's about 1,800 parts per million. So left to right, over the speed bump, engine restarts, large spike of NOx. The same vehicle, if we look at its hydrocarbon emissions on the RDE route, I'm going to show you here in orange the engine out emissions measured in a position which is close to cylinder number 1, so it's biased towards just one cylinder's emissions, and in blue will be the tailpipe emissions after both of the catalysts on this vehicle. But this is at the point on our RDE route where we emerge from the urban section into the rural section. During all of the urban section, the vehicle was running on its battery, so there was no emissions to see. So effectively, this is the engine's cold start. So here we go. We've got lambda in green again. Here's our cold engine start in orange. You see each of these pulses here, what looks like noise on the orange is actually each individual engine firing exhaust event. You can see in blue that's heading towards 0, so it's operating its catalyst heating strategy. This part of the drive is rural, so there aren't many transients in it. Apart from that hard acceleration on entry to the rural section, the catalyst heats up very quickly. Possibly one of the worst vehicles I've ever tested on the London route is a Euro 5 diesel, so no NOx after treatment at all. It has EGR on it, but it is very much challenged by entry to the motorway on an up-ramp, because on the up-ramp you are absolutely demanding maximum power because you want to join the motorway at 70 miles per hour. Each of the gear changes, you can see the NOx drops and then rises again. Here we're measuring both total NOx and NOs, and the cumulative NOx calculated from the ppm and the exhaust mass flow rate is shown in red. you can see here that we are dropping 1 gram of NOx every 8 seconds. So this is an extremely high level of pollution, but concentrated just into that area because of the very high power demands required. So probably EGR is just switched off at this point anyway. This is not, this is very harsh acceleration, but it's the way that people will drive because one needs to approach a motorway to join the motorway at motorway speed. And if that's on an up ramp, then this is going to cause NOx emissions. And when I showed this to Transport for London, they did say that what air quality monitors they have in that area and at Swiss Cottage do tend to show some quite high levels. So I mentioned before that we had this test vehicle, which was Euro 60 temp diesel. So this is extremely clean. It's fitted with an SCR system. In fact, if we look at a schematic of its after treatment system, after the turbocharger and very close coupled, there is a passive NOx adsorber, which is a catalyst which is, it acts kind of like an oxidation catalyst, but it has an added feature that when it's cold, it should be able to trap some NOx, and then when it warms up, it releases that NOx onto an SCR system. So even during cold start or cold operation, the PNA is supposed to trap some NOx and then release it at a time when the SCR and the SCR coated DPF are able to cope with that released NOx. The vehicle has its own NOx sensor, and on the vehicle we took a sample point near to its own NOx sensor, and we measured fast hydrocarbons, NO, NO2, CO and CO2. Now there wasn't much to see in terms of hydrocarbons on this diesel, so what I'm going to concentrate on is really the NO and the NO2. Notice that we did all of this work upstream of the muffler because we didn't want to be smoothing our data out because of the volume trapped in the muffler, and we did a lot of work on this vehicle in controlled conditions on our chassis dyno, where we also compared the output both to an FTIR but also to a MEXA conventional analyzer, which was also measuring the tailpipe data. So we had some cross correlation there as well. Here's some photographs of the hardware that we installed. So here is the vehicle's own NOx sensor, and right opposite that, this is our sample pipe where we were taking our data. It's only about maybe 15 centimeters long, and this pokes through into the passenger footwell upstream of the muffler, so that we are not mixing our sample before we sample it, and then we put our fast analyzer sample heads in the passenger footwell. On the London test, you can imagine that during a lot of urban, sluggish, slow driving, the catalyst temperatures, and this is data that we took with an independent K-type thermocouple that we'd also put in the exhaust, you can see how cold the temperatures are. So they're down often below 150 degrees, sometimes 100 degrees. So an SCR system really isn't going to do much at that point. It's not going to be very active. And yet, the NOx emissions from that vehicle were really quite low. But there is one section where there was a bit of a surprise, and that is back at our old friend, the on-ramp to the motorway on the M1. Now during this 1 hour 45 minute very slow driving, we will have been filling our SCR system with ammonia, but as we accelerate onto the motorway, we're heating our after treatment system up very rapidly, and the SCR system simply can't hold on to that ammonia. And the great accidental thing about solid state NOx sensors is that they are cross sensitive to ammonia, whereas the fast analyzers are not. And therefore, if we subtract the fast NO and NO2 from the vehicle's own NOx signal, we can yield a measure of the ammonia. And we know that on that up ramp onto the M1, onto the motorway, we emitted about 2 grams of ammonia. By looking at the difference between this grey signal in the top, which is our NOx sensor, and the NOx, which is being detected by our own analyzers, the difference between the two is down to ammonia. And we've double checked this by repeating this part of the cycle on the chassis dynamometer and measuring with the FTIR, measuring the ammonia at the tailpipe. Ammonia is a very difficult gas to measure because it's very sticky. You need to have electro-polished sample lines. Everything needs to be hot, otherwise you get a lot of hang-up. And we would be interested to know if anyone thought it is worthwhile us developing an ammonia sensor which has some fast response characteristics. If we were to use this method, it would be no faster than the response time of the NOx sensor. So it would have a response time of about 1 to 2 seconds. But we've heard that the ammonia being emitted from a three-way catalyst, as the catalyst warms up, can, in the gas phase, be quite highly transient. So I'd be interested to know this as a development project. So the equipment has also been used on board buses. A lot of interest from local authorities and air quality experts on the effect of buses, which are allowed into clean air zones. But buses also undergo a fair number of transients. Here is some data from a bus in Oxford approaching and departing from a bus stop. So the instantaneous NOx is being shown in the upper graph and the exhaust temperature is being shown in the lower graph. And the great thing about a bus is when it slows down, diesel fuel shut off, but the engine's still rotating. So it's basically pumping cold air through the SCR system. So the temperature is dropping at that point. So we stop there, the engine returns to idle. Then passengers get on, and as we accelerate away from the bus stop, there is a large amount of NOx emitted as we accelerate away, and also there are large spikes at the gear changes. So when we look at the correlation with the bus route and the map of Oxford, we can see that the main emissions of NOx occur right next to bus stops, which is where people are standing waiting for a bus. So the advice there is, if you're waiting for a bus, if one arrives, even if it's not your bus, get out on it anyway, because otherwise you'll get a lot of NOx being emitted as that bus departs. And finally, there's been a lot of debate in the UK about switching off your engine. Don't idle your engine, and rather large fines can be imposed. But from all the work we've done at Combustion, we know that stopping and starting of engines can produce quite significant spikes of emissions, especially NOx. So we took a few candidate vehicles that we have at our disposal, which are public vehicles. They're not owned by any of our customers, and we studied the restart emissions. So by restart, I mean, if you were to leave your engine idling, you would be producing, this is an idealized schematic I'm showing here, you'd be emitting what you might call a steady amount of idle NOx. But if you stop the engine and you restart it, when you restart, the emissions from the vehicle will tend to overshoot, then undershoot, and then the vehicle will arrive at the same idle position. But there must be some equivalent idle time to that restart. And if you were to stop and start your engine a lot of times, you're going to make the air quality much worse rather than just leaving it at idle. So the calculation we're looking at is the time of C. That C, that area C, is the equivalent to A minus B. That's the equivalent idle time to my restart. So T is our, if you like, our worthwhile switch off time. If you are not switched off for as long as that time and you restart, you're only making matters worse. So if you look at that time on the Euro 5 diesel car that I showed you earlier, the equivalent time there comes out to about 30 seconds, which means if I pull up to some traffic lights, if I'm not going to be stopped there for more than 30 seconds, I'm making matters worse by switching this vehicle off, because when I restart it, I'm going to be emitting 30 seconds of worth of idle NOx emissions. And we looked at other vehicles as well. We looked at that Euro 5 diesel, and that has some variation in it depending on how you've been driving, but it's about 20 to 30 seconds of idle is the equivalent from that Euro 5 diesel. A Euro 6B passenger car diesel, its equivalent idle time is only 3 seconds, and that's because modern diesels are fitted with automatic stop-start, and their restart emissions have been very, very carefully calibrated to make a restart very clean, which is not the case with the Euro 5 diesel. And with a Euro 6D temp diesel, when you restart that engine, there's virtually no NOx when it restarts, but actually there's virtually no NOx when it's at idle either. But it's strange how seldomly that vehicle actually activates its automatic stop-start. And this because it looks at a number of parameters. The electronic control system, the brain of the vehicle, looks very carefully to check that many parameters are in their correct state. So the battery state of charge is good, the ammonia storage capacity, which is being called up from the model, it assumes that's good, the temperature, the catalyst temperature is hot. It checks maybe 20 different parameters before it thinks it is okay to automatically switch off. So really, forcing an engine to switch off which doesn't want to, especially in an older vehicle like a Euro 5, is probably the wrong thing to do, and it's quite unfair that you'd be fined for doing that. And very finally, so we're constantly developing new equipment. This is a one-channel cheaper version of the fast FID, the fast hydrocarbon analyzer, which I showed right at the start and on the Prius when we showed the hydrocarbon start emissions. So this is something which I was just wanting to mention because we've shipped one of these systems to my colleague in Shanghai. If you wanted to try one of these out, this is a little bit slower than the fastest version of the analyzer we do. So we have a FID 600 system, which has a 1 millisecond response time, an HFR 500 version, which is also 1 millisecond, and which are 2 channels. This is a cheaper single channel system, but for engine calibrators who are looking at cold start calibration, this is exactly what this is aimed for. So if you're interested in one of those, or you've got any questions, here are my contact details. I think Peter is going to field some questions now if you've got some, but here is also the contact details of my colleague Li Chan, who is in Shanghai, and some of you may know him already. And with that, Peter, I will stop sharing, and I haven't been looking at the time, but I'm hoping I am almost on time.
Yeah, thank you very much, Mark. Yes, you are on time, and what a fantastic presentation. I thoroughly enjoy that. And I normally expect very high quality data from combustion, but this is another level, I would say. Yeah, thank you very much. So should we start with some questions? Shu, do you have any question?
Yeah, first of all, thanks, Mark. I'm really impressed that this is probably the best quality, the most interesting emission analysis presentation I've ever seen so far in these years. And then so basically I'm just quite interested in, is there any, it's really important for calibration engineer to have rapid response as fast as possible for lambda and the NOx behavior. Do we also have the other examples, for example, the advantages of using this transient emission analyzer and then doing the calibration or something? What happened is in the PAMS test, we're having a significant benefit, or maybe other advantages does the transient emission analysis have, but PAMS kit not that good at?
Yes, so you remember the slide that I showed you? I'm not sure if I'm able to share again, but I will go back to the slide that I showed you from Marla Powertrain, where I showed you the PEMS versus the MEXA and the FTIR and the, let me just see if I can share my screen again. Our problem, I suppose, is that we don't own at Combustion any PEMS equipment. We
Oh.
we have a lot of MEXAs, so standard emissions analyzers, CVS tunnels, etc. And we've got a lot of data from a variety of different applications, not customer data, but data that we've taken ourselves, showing the variety of data that you can get, which is very fast. Can you now, am I now sharing my screen again? Can you now see this?
No yet.
Hold on,
Not
let me
yet.
just check. Let me just check I'm sharing the correct screen. Try that. Okay, see it again?
Yeah.
Yeah.
Lovely, okay. So here is the spike in blue. Exactly the same gas is being recorded by PEMS in yellow, and with a conventional analyzer in red, and with an FTIR in grey. So this is all the same emissions data, but the advantage of the fast is shown by the fact that this spike is measured and can measure 2,800 parts per million. And not only that, but it is positioned already, because it has virtually no delay, it is already positioned with the lambda trace. So you have correlation between not only lambda, but all of the other engine parameters that you can log. They're all there already. I just haven't displayed them here. With the PEMS equipment, it's still accurate. The data is still there, but it's all mixed and smoothed and delayed. So it's very difficult from that PEMS data to correlate with what engine parameter is causing that spike of emissions. So during this presentation, what I had to do was to try and choose just a subset of data that I could easily show with you. We've got some nice data showing the closed loop lambda control, okay, which oscillates a gasoline engine slightly rich, slightly lean, slightly rich, slightly lean at about 3 Hertz, for example. If the catalyst is aged, on the lean half cycle, you can see in the tailpipe, if you have fast NOx, you can see on every lean half cycle a little spike of NOx coming out. I haven't got this data here, but if you or anyone else wants a kind of dedicated separate presentation, I can show you that data as well. But we've got a fair amount showing the response from a conventional analyzer, really not seeing those very short duration transients, and the fast analyzers which can show that. But this slide I'm showing right at the moment, which was done using Mahler's PEMS system, kind of shows the benefits immediately. Does that answer your question?
Yeah, thank you so much.
Yeah.
From calibration point of view, to be fair, just say a little bit more. If we ignore the blue one, if we do not have the blue one, we only have the PEMS, the yellow one I told, it will be hard for us to track where is exactly the error. We need to do some calibration changes.
Yes.
But that rapid response will be really, really helpful for calibration work.
Yes, and remember, this calibration work it's probably not going to be done on the road. This calibration work is going to be done in the lab under controlled conditions, but you would still, you can use the same equipment in the laboratory, running repeats of these particular transients to try and pin down, because you as a calibration engineer, you know how many hundreds of parameters you've got that you can play with, but it normally comes down to the top 10 of EGR, so valve timing, spark timing, fuel injection timing, and lambda control. And mostly it's lambda control that you would go after first.
Yeah.
Mark, I have a follow-up question on this. So I think to emphasize on the calibration aspect of this transient response of the analyzers, but from a emissions engineer's point of view, for compliance, product compliance point of view, how much cumulative emissions differences it made if we use a fast analyzer compared to PEMS and standard equipment like MEXA and FTIR?
So yes, that's a very good question, because this equipment cannot be used as a substitute for PEMS. The NOx system is actually, its specifications are within range, but because the PEMS system has to contain a variety of, so you put your PEMS system on and you will be able to measure NO, NO2, CO, CO2 and hydrocarbons, for example. If we put our CO analyzer on here, the drift of our CO analyzer, it's 1,000 times faster, but it's 10 times more drifty than a PEMS piece of equipment.
Okay.
So from that basis, you would not be able to use our equipment for legislative certification purposes. And that's not what it's designed for. We've designed it so that maybe you will go out with your PEMS equipment, you'll come back and you'll see that you have exceeded your allowance on NOx, for example. Then you would take your fast RDE equipment out and you would look for the spikes. You would try to identify where and why am I exceeding my NOx. So you're really just using it as a calibration tool. You're not using this for certification work. It's really a complement to the PEMS equipment, which is certified equipment. This is really just a calibration tool. So it's not a substitute, but that's a good point. Thanks for raising that.
No problem. So when you mentioned that the PEMS is still accurate, so we know that today the PEMS kit got a certain difficulty in being consistent, and therefore there is a PEMS margin in the RDE requirements. And if we're projecting to the future legislation probably will narrow down this kind of margin. But how do you perceive these developments of the emission analyzers for the certification purpose and also for calibration? Is there any convergence between the two with a much better accuracy and the transient response, but also having a low drift?
Yes, that's what everybody is after. That's exactly what everybody wants. This is the beautiful panacea. Unfortunately, you see, you've got the big players in the conventional market who will follow, and sometimes they will be involved in the discussions about the legislated what is possible in terms of measurement. Combustion, you know, we're 65 people, we're a bit player in this market. We come up with some interesting tools, but we're not going to drive this market. But we are also after accuracy, but we're especially after time response. We're especially after being a tool for the calibrator, but it's a kind of different market. So you will have Hariba and AVL and others who will make PEMS equipment, and they will make large quantities of good quality PEMS equipment. But we know that as time goes on, their drift, their reliability, their stability, and to some extent their time response is improving. But if you have PEMS equipment which is bolted onto the tailpipe of a vehicle, they will always be limited by the mixing which is occurring in the vehicle's muffler. So I could put my fast response equipment at the tailpipe of the vehicle, but I'll probably not see anything very fast because I will always be limited by the mixing volume which is within the muffler. It's really, you notice that the first vehicle I showed you was an old Euro 4 vehicle. That's because my colleagues at Combustion would only give me an old vehicle because they knew I was going to put a drill through the floor to put my heated sample line in before the muffler, after the catalyst, but before the muffler. Once they saw the data and they thought, oh, this is quite interesting. Yes, maybe this is useful. Let's put another hole in through the, you know, on a vehicle you have two steering column holes. Yeah. There's one which is for the actual steering wheel. There's the other one which is for left-hand drive or right-hand drive vehicle. There's just a plastic blocker in there. You take that out and then you can put a sample probe through into the engine bay and get to the before catalyst position. I know that I think with PEMS equipment, you're allowed zero drift on NOx of something like, quite a lot of parts per million. I know that from the RDE tests we do here with our NOx equipment, we drift by normally a maximum of 1 ppm. So I know we are well within the specifications of drift for NO, but what we can't do is our drift for our CO is just too high. We actually sacrifice stability in order to get our 1,000 times faster. And that's really because we are absolutely focused on the transients, not on the accuracy of zero after 2 hours of driving. Okay. So it's really just a calibration tool.
Okay. Really looking forward for any future development in these advanced analyzers. And then also, as you touch base on the CO topic, I know a lot of CO emissions at the moment are just monitoring. Is that the reason that you just mentioned about that CO, because of reliability of the data, so CO is not really being enforced as a legislative RDE emission?
Well, it's interesting you should say that, because the seminars that I've been to by European legislators and the European Commission, they said that the target in future was going to be particles, so sub 23 nanometer particles. So, you know, we've been very interested in that. So we've been developing products looking at down to 10 nanometer solid particles. Ammonia, and I mentioned ammonia before, so we are interested to see if there is any market and any interest in the measurement of ammonia. And we know that there are solid state sensors out there which are dedicated to ammonia, but we also know that there are questions over cross sensitivities to ammonia, the pressure, temperature effects. I'd be interested to know if anyone is interested in ammonia. Is ammonia actually moving fast enough that it is worth measuring it with any kind of speed? Or can you just stick with QCL and FTIR? Maybe that's good enough. And CO. The one thing they did mention also was CO. They said CO has had an easy ride for the past few years, and it is likely that they will bring down the limits on CO. However, because I have been to no conferences where people have been speaking from government since COVID started, I don't know. Who knows what's going to happen in the next year or two? We're pretty sure things are going to be delayed, but where the focus is going to be, I don't know.
Okay, thank you. I think that the questions follow out really well, because you mentioned the PN, and then you haven't shown any PN data or PM data in your presentation. Could you comment some of the PN measurement difficulties, and also maybe projecting to, for example, Euro 7, which a lot of the articles speculating we're going to drop the PM measurement down to 10 nanometer maybe, and how is that going to impose any difficulties in either measuring it and then also the calibration activities?
Sure, that's right. So I tried to limit my discussion here to things that we can do on board. Okay, we have a fast response particle size and number instrument which is called DMS 500 instrument, and there are a lot of these in the UK, in Europe, in the US, and a lot of them in China and Japan as well. This will measure particle size and number from 5 nanometers up to 1,000 nanometers. So easily taking in the solid and liquid particles over that range, and with a response time of about 200 milliseconds. So not quite as fast as the gas analyzers, but fast enough to calibrate a cold start and calibrate some gear changes. Within the last 2 years, we developed an accessory for this called a catalytic stripper, which takes the particles and evaporates and removes any of the volatiles. So any of the nucleation mode particles, which are generally fuel which has just recondensed into an aerosol, it strips those out, and the only things that are left behind then are solid particles. Now these solid particles, which are down at 10 nanometers, if you do not use the catalytic stripper, then they would be lost in among the liquid fuel. Okay, now the liquid fuel, the aerosol, the volatiles are not counted in the legislation. So if the legislation comes in that solid particles down to 10 nanometers are required, then we can measure that for you fast and with a size spectrum. I don't have this as part of my presentation, otherwise I'd show you a lovely bit of cold start data from particles from an engine. We should be able to measure that for you, yes. But we can't put it on board. It's a big instrument. It's a heavy instrument. We've not yet got that on board. But if for calibrating in the lab on a chassis dyno, call me.
Yeah, I think you predict the question actually coming. Someone just asked from the audience saying, is DMS 500 actually too large to put it on board? I think you answered the question. Yeah.
You know, you could use it on board a truck. I mean, when I say it's heavy, I mean it's like 80 kilograms. It's like no, in fact, it's 80 kilograms plus its vacuum pump. It takes a lot of flow as well. It's kind of impractical. And if you were to put it on board, you would need a very stable platform because it's vibration sensitive as well. And you don't want to start showing up what appears to be particles, and really what they are is the vibration from the road coming through.
Noise, yeah.
That's right, that's right. So there are other instruments you can get, but I don't think, well, so far I have not yet, myself, I'm not yet aware of something that can measure down in the 10 nanometer particle range accurately in terms of size and number.
Okay, thank you very much. I think we have someone from all audience want to ask the question to you directly. So should we invite our?
Yeah, can I invite my friend?
Yes,
Hello,
go
Nathan.
ahead. Yeah.
Yes.
Hello, I'm Ignacio Navarro. I work in diesel emissions actually, so your presentation is brilliant for me. As you said, the fast analyzer is mostly planned as a calibration tool because I've got experience of having to collate loads of data from different sources and then having to align it and having the feel the pain of having to align it. Is it designed to connect to calibration tools such as Inca or Vision? So it can go straight away into the recorder?
Absolutely, yes. So, I mean, the equipment that we have that I've been showing here just has regular analog outputs. So you can stream that into whatever data logger you have. But the joy of it is there is virtually no delay time. The delay time through the instrument is, let me see, it's about 4 milliseconds or something. Okay, so the real delay time that you would have to deal with is the time taken from the gas to leave the engine and arrive at the sample point. Okay, so you're looking at actually, if am I still sharing my screen with you? I think I am.
Yes.
Yeah.
Because I want to show you some uncorrected data, some data where there's been no correction made at all. Now I'm trying to find out where I've put it. Was that data which I took showing the engine out and tailpipe at the same time? Yeah. Okay. So can you see my screen?
Yes.
Yeah. So you see the red and the blue data where my mouse is pointing. There's a delay through there of about 0.3 seconds.
Mm-hmm.
That is a real delay of the time taken for the gas to pass through the catalyst. So the red spike at 1049 and the blue spike at 1049.3, that is the 0.3 of a second taken for the gas to, the spike of gas to appear at the engine out and at the tailpipe location. But there is no delay been put in compared, this is just logged in real time, no delay correction required because you know, it's all like recorded in real time. So I know that the CAN data that we have here from the lambda sensor of the vehicle, it's a bit steppy, it's not very good resolution, but I don't know, maybe your CAN output is better temporal resolution than this. But you know, you can see the wobble here on the engine out and the wobble coming through on the tailpipe. This is a gasoline engine, obviously it's not your diesel application. But you can also immediately see the engine parameters and how they correlate. And this is without having to do any data alignment. So as long as you just log it all into the same data file, you can just open up and should be able to interpret it immediately without without sliding data backwards and forwards by a number of seconds. It's immediate and it should be obvious.
Yeah, there is another good use of it actually. For those who have experience with it, being able to connect the calculated mass flow of the PCM with the ppms of the sensor allows you to calculate the actual flow per second, because in some occasions you may have very high NOx in the measuring point, but there is barely any flow. So the actual tailpipe is really low. Yeah,
exactly, and that's a very good input. So the software that we have written for ourselves to interpret this data, we've got all the calculations are open access, so I can send you the calculation we've done for this. But if you're very lucky, the ECU will actually give you or will report to you an exhaust mass flow rate. If you're not so lucky, you will have manifold depression, you will have the RPM, you'll have to make some, you know, some assumptions to the volumetric efficiency, but you can work that out. But the joy of it is you can you can multiply and operate on those parameters in real time. So as we're driving around, as long as we've got our software set up, we can see the instantaneous mass, as I showed you from the awful diesel engine approaching the M1 junction. Here we had, from this vehicle, we had instantaneous exhaust mass flow reported from the ECU. And so we could immediately, on board the vehicle, combine it and get this red trace, which is our cumulative mass. And as we accelerate up this up ramp, you can see the scary amount of NOx being produced. So we're going from 47 grams of NOx to 48 grams of NOx in 8 seconds. Yeah, so you should be able to get the same as this. Does that answer your question?
Yes. Thank you very much.
Where are you anyway? Have you got some of our equipment already? Are you in Spain?
No, I'm actually in Essex. I
Okay.
work in Ford actually in Essex.
Okay.
You must be familiar. Yeah.
Okay.
Yeah.
But okay, well, this is, you know, you should come visit. I'll take you a ride in this scary car of yours, and you can log this data yourself. You can see what it does, or ask Tony Collier. He'll tell you.
Yeah, I know him well.
He'll tell you it can't be done.
Okay, should we invite our next guest for the question?
Dr. Song?
Hello. Hi, Mark. Yeah, it's
Oh, hello.
Hello, hi, Mark. Yeah, it's a very good the presentation. I'm very interested in that. And I have a couple of questions. Yeah, the first question has been asked by Natural already. Okay. Another question, because I used to be a calibration engineer, you know, but for these few years, I have stopped doing the hand-on calibration work. I don't know, you mentioned like you from the fast response measurement, and then they put the back to dyno and to improve the calibration, to eliminate the spikes, yeah, emission spikes. So I was thinking, if it's very useful, if the PCM software has some function or features to have the transient correction. So the vehicle calibrator don't have to go back to the dyno and just to do some modification on vehicle and look at the test results again.
So we have some customers who come and they either cannot afford to rent our chassis dynamometer, or the chassis dynamometer is so busy that we cannot put their vehicle on for any significant amount of time. The thing about putting the vehicle on the chassis dynamometer is that we also hook up a rapid cooling system so that we can run a drive cycle and then we could rapidly cool it, and after only 2 hours we can have another representative cold start by circulating cold air and cold coolant around the engine. In those situations, customers will come to us with an open ECU and they will try to calibrate the vehicle while we are driving around Cambridge, and they have got me to go around the same loop of a road. So generally I'm driving and making sure that the analyzers in the trunk are working at the same time. The guy that's sitting beside me, the calibrator, is looking at the data and he will say to me, okay, let's go over those set of speed bumps again. Then he changes something, we pull into the side, he changes something, then we go around the speed bumps again. But you have to make sure that you are approaching those speed bumps with the same kind of catalyst temperatures that you did the first time. Because if you then generally just sit in a lay-by while you are making the calibration changes, you may be approaching those speed bumps with a slightly cooler after treatment system, and I don't know, maybe the coolant and then the oil temperature has dropped somewhat. So the repeatability is never quite so good when you're trying to do this with an open ECU and trying to do the calibration on the cheap. But yes, it is something that we have had to do, but it's very much more. In fact, if you come with a car which is, let's say it's its first calibration, so a development vehicle with a development calibration, you can make some quite good significant improvements before you get onto the dynamometer. So in terms of cost saving, you can do a lot of the calibration, but it's the refinement of it which really needs to be done in controlled conditions. Does that answer your question?
Yeah, yes, yeah, very good. Okay, understand. Thank you. And another question is, you mentioned that you drove 3 cars in London, and 2 of them are the PHEV and the Euro 6D temp. So did you compare the emissions between the 2 if they all optimized already?
Well, those 3 vehicles were all production vehicles. In fact, the Euro 6B PHEV vehicle, so it was gasoline Prius basically, it had only got 150 kilometers on the clock. So it was a really new vehicle, okay? But it was, you know, it had been bought from a showroom, absolutely new. It had been given to me by Loughborough University, just for a few months, just to play with. And then the Euro 6D temp vehicle, that was purchased by Combustion. It was baselined on our chassis dynamometer and around the Cambridge RDE cycle for a few months. But when it went to London for those tests, it had also only done about 300 kilometers. So both of these systems should have been as good as new. So, you know, it wasn't as though their calibration was raw or was not refined. It was as good as new and should have been compliant with emissions legislation. And both of them were. We did do some WLTC and some NEDC cycles on the chassis dynamometer, and they were both very compliant. The diesel vehicle, the Euro 6D temp, was extremely compliant. It was 3 times under the limit that it needed to be. And the reason for that is that there is a strong expectation that the PNA will degrade over time, and we've also seen that. But that's another presentation. But
all right. Okay. Thank you very much indeed.
Pleasure. Nice to see you.
Thank you.
Thank you, Mark. So I think in your presentation, you mentioned quite a bit of conversation with Transport for London and then showing the evidence of what the real emissions are. So I think the part you didn't tell is what's their response?
Well, I don't know what it's like dealing with politicians, really, you know. I mean, I suppose these aren't politicians, they are civil servants. So the first thing that they want answers, and they want easy answers, and they want nothing too contradictory. So I'm not a politician, so I told them everything. I told them, for example, it's not a great idea to get old diesel engines to switch off and then switch on very quickly. They didn't like that at all, because that's not a simple message. So they didn't like that at all. But I was so keen to show them this data, the fact that things have improved so rapidly. I thought this was a wonderful thing to sing from the rooftops about this data, because the main reason I wanted to get this across was don't stop engines coming in. You just want to make sure that older engines, it's clear that older engines are producing, you know, 15 times more NOx than a modern diesel engine. So don't go mad and say, okay, no engines can ever come into the city again. Just take things as they are. The data is showing, and you have to also appreciate that We've only got 3 sets of data here. Really, you need to do this on different days, the same route on different days, with a much wider variety. I was kind of fishing for work from them. I wanted them to commission a study using combustion equipment and using combustion personnel, which is much longer, even though the drive is very, very boring. But the take-home message from this is that new diesels, they are so clean. New gasoline engines, I mean, this Prius that we showed here, it had a few bad areas, but they wouldn't be compliant. That vehicle would not be compliant with RDE legislation, okay? And it didn't need to be. That was a Euro 6B vehicle. It only needed to be compliant to the NEDC. But still, it's a fantastic vehicle, you know? So I just wanted to let them know that, that things are moving forwards. And even if they did nothing, by the time the old vehicles retire and come off the road, the new fleet of vehicles are so much cleaner. So don't panic. Maybe put in place measures to penalise the older vehicles and encourage old taxis off the road. But the new vehicles are fantastic. So don't panic.
Okay. Thank you for your comments. For our audience, if you want to join our discussion, please raise your hands. So I think we have a few more minutes. So regarding the speed bump analysis you have done, especially around schools, you said the you're having a lot of speed bumps. The intention is trying to keep it safe for the school area, but actually increase the emissions. Is there any better solutions you can suggest for that, or not from the plannings from this of the infrastructure, or from the engine operation on transient to deal with this kind of conditions? Is there anything we can do?
Yes. So this is something that Transport for London did agree with quite easily. They were immediately convinced by the fact that speed bumps are bad. They're bad in terms of they hurt the suspension of the vehicle. They know it was bad in terms of air quality as well, because there have been studies done in the past. But just how bad, you know all of these dash cam videos I'm showing you there. The reason that the air quality and the Transport for London people can get the message so easily because it's all eye candy, basically. This is all, you know, this is just easily understandable because there's so much moving images and it's like watching TV. But the thing I was able to tell them is that three-way catalysts in a gasoline engine, they're really actually very good at taking out a lot of the pollutants. And I emphasized to them the fact that the emissions during this steady state operation in the bit of video that I'm showing you right now, it's basically zero because catalysts are 99.9% efficient. It's only when you upset them with a hard acceleration or some harsh transients, like a speed bump. And remember, speed bumps are forcing transients onto the drivers. You have to slow down. And when you have slowed down, you're going to speed up again. That's just human nature. The way that they will probably have to go in future is put in average speed cameras. So over the entirety of that road, you have a gate camera at the start, a gate camera at the end, looking at your number plate and dividing distance gone by time taken and issuing a fine, or at least flashing up a sign to say that you've exceeded the speed limit over that time. They were very easy to understand that. The other thing with that interaction with Swiss Cottage and the speed bumps in London, which even with a Euro 6B Prius, that caused that interaction. Remember, Swiss Cottage doesn't have any speed bumps, but there are a lot of lane switching and 2 lanes going into one and a lot of congestion. Just a little bit more attention to, you know, road layouts might help to reduce the NOx emissions around there. But in terms of the calibration, you know, when you know with gasoline calibration that when you restart after a diesel fuel shutoff, you normally put in a portion of what's called rich purge. That's what it's called in combustion anyway, because you have been washing oxygen over the three-way catalyst during the diesel fuel shutoff. You need to reload an amount of reductants back onto the catalyst by some rich operation. But the time taken over which you can load with CO and hydrocarbons, you can load it to the point where CO starts to appear out the tailpipe. And again, a fast response CO analyzer just after the catalyst, after a rich purge, so you can count the number of seconds until the CO starts to lift up. Using that to calibrate your rich purge interval can also be quite useful.
Thank you very much. I think that's a very good answer. And also, another type of emissions that were not mentioned about this speed bump is the brake dust. And then there's another type of the particular emissions which I hope they are going to pay more attention to, not just on the tailpipe, because it's so clean now, I would say.
That's right, that's right.
Yeah.
And they are significant, and people are turning their attention to that. So we've used the DMS system for looking at brake dust. There was a sampling system developed, which was like a mudguard, which was over the wheel of a car on a chassis dynamometer, and you will get a different size of particle coming off the brakes. If it's gentle braking, you get a certain size of particle. I think it was about 600 or 800 nanometer diameter. But when there's hard acceleration and the brake pads get very hot, then you start to boil and burn the resin that binds the material together, and you get a different size of particle associated with the burning resin.
Fascinating, fascinating. I think we have a audience guest raising his hand. Fu Qian, do you want to join our discussion?
Hi, Mark. Hi. I don't know if you can hear me.
Yes,
hi.
yes.
Hi. Thank you for your presentation. It's marvelous. And I've actually finding the London's ULEZ and for the CSAE as well, they're using a quite stupid method to regulate the cars and entering the city centers, and which I found. They regulated, for example, for NOx. They set a standard like 60 milligrams for petrol engines, and as long as your car is below that amount, you can easily drive like a 90s, very first generation Toyota Prius into the city center. I don't think that's quite true and quite real. Can we find, because I'm a data analyst, can we probably find a general conclusion by like aging cars, is emissions, how that would affect the well, like the age will affect the emissions, NOx and COs and other things? Probably we can make a suggestion to the government that they must do something to change the quite I would say quite stupid method. That's my first questions, because yeah, your findings is quite marvelous. And the second question is, can we say, because you've been finding the PHEVs got some advantage on, because when you accelerate the cars and the yeah, the amount of NOx and other types of the emissions will goes up. Can we say probably like the range extender engine types of engine would be better, and they can as clean as pure electric vehicles probably in the future? Well, yeah, that's my question. Thank you.
Okay. I think first of all, your questions make my editing work a little bit more difficult, but that's fine. Mark.
Okay. I'll take your second question first, because I've forgotten your first question, but we'll come back to that. Yes, so range extender engines. There's a wonderful piece of marketing has been put out by, I can't remember who it was, have been starting to term those range extender engines as self-charging hybrids. but it's not really self-charging. There's an engine in there. Let's be quite clear about it. There's an engine in there. The great thing about range extender engines, though, is because they're decoupled from actually driving the wheels. When they start, the ECU can put that engine with whatever load, speed, air-fuel ratio it wants to heat up the catalyst as quickly as possible. So potentially they can be really quite good. We have done a bit of testing at combustion of vehicles with range extender engines, and it's really, it's really the startup transient that needs to be calibrated. But there's still a job to be done there, and it will still emit, albeit quite low levels of hydrocarbon, CO, and NOx. So potentially that's they're very good, and they're also quite small as well. They're quite low capacity. So yes, they can be. But the one of the features, depending on the vehicle involved, you can sometimes have a kind of limp home mode, whereby you have run out of electric charge completely, and you have to drive on effectively indirectly, but with that motor, and it all comes down to the same. Even at steady state, the lambda control, if you don't get that quite right, if you have very deep oscillations of air-fuel ratio and your catalyst is not sized correctly or has been poisoned, then you can get some breakthrough of NOx during the lean excursion. So all of this needs to be looked at as well. Your first question, I think, related to the classification of vehicles and how a different method of classification might be used. So I know that what the Transport for London are looking at are the kind of published figures by the various manufacturers, sanctified by what would it be? Not the DVLA. Whatever is the published CO2, grams per kilometre and NOx per kilometre. What they are also, though, looking at is data which is being produced by emissions analytics, which is produced purely on the background of their own PEMS system, and they are looking at they are publishing their real world NOx emissions figures. I don't know how representative that is. This is the whole defense that the car community is putting up against emissions analytics is, well, how can you rank my vehicle if you've only taken it for 2 or 3 runs, and each run may be quite different because real world driving is different. That's the whole point about it. If you want to do everything on a level playing field, you need to run some sort of drive cycle, and the WLTC is a pretty good exercise of most vehicles because it has some quiet points, it has some hard transients in there as well. So going forwards, we can see a trend towards anecdotal or evidence which is produced from third parties who are ranking, putting vehicles in different rankings and publishing this and making this available to the public. And Transport for London are very, very much enticed by that method.
Is it something like the air index?
Correct. That's exactly it. Yes. Yes.
Yeah. I am aware that ACEA also having a huge database for real-world driving emissions. So if people on the audio are interested in this, you can go to ACEA to find out a bit more about this, and also search for air index, I would say. Yeah. I think, Mark, thank you very much. I think time is about coming to the end. We're slightly over, but I think we have a very enthusiastic audience, and what a fantastic presentation and the Q&A section. Thank you very much.
It's a pleasure. Thank you all for coming. And yeah. I think this is going to be available on YouTube later.
Yes, you
right?
will. Yes. Yeah. So good. Yeah. So looking for our YouTube channels if we want to replay this, and also. In the end, I want to raise this again. We're going to host our annual conference on 31st of October, and we're looking for active sponsorship and collaboration if you're interested. So please reserve your day for our annual conference. Again, thank you, Mark. Thank you, everyone. Have a nice day.
Have a nice day. Thank you. Bye-bye then.
Thank you very much. Thank
Bye.
you.
Thank you very much.